Good morning, students. Our today's topic is Gram-Smith process. In this process, we are given a linearly independent set in an inner product space, and we convert it into an orthonormal set given by the sequence Ej. Here, we are given xj, that is a linearly independent sequence in an inner product space, and we will convert this sequence into an orthonormal sequence ej such that the span of the new sequence is same as the span of the sequence which is given to us. So the procedure for this is, in the step 1, let us form the first vector which is normalized by taking the first vector from the given sequence. This is a given sequence. We take the vector x1 from this sequence and let us define e1 is equal to x1 divided by its norm. Now, because x1 is non-zero vector and therefore this is possible, every singleton set is linearly independent, and also if we find the inner product of this vector with itself, we can see that this will become inner product of x1 with x1, that is x1 norm square divided by x1 norm square. This will become 1. So norm of the vector e1, that is 1. So in the first step, we have obtained the first member of our orthonormal sequence. Now in the second step, let us define v2 by x2 minus inner product of x2 with e1 into e1. Firstly, we will show that this vector v2, that is not equal to 0. Now if we take this vector is equal to 0, then we get x2 minus inner product of x2 with e1 into e1 is equal to 0. Now substituting the value of vector e1 here, we can see that the inner product of x2 with x1 divided by x1 norm square into x1, that is equal to x2. It means x2 is some multiple of x1, but that will give us a contradiction because x1 and x2 are linearly independent vectors. So this contradiction proves that the vector v2, that should be not equal to 0. Now we will prove that this vector v2 is perpendicular to the vector e1. So let us find the inner product, substituting the value of vector v2 here and using the properties of inner product, linearity property. By that property, this will become inner product of x2 with e1 minus this is scalar, that will come outside. Inside we have inner product of e1 with e1, that will become e1 norm square. This is 1. So we get the inner product of vector v2 with e1 will be 0. Because the inner product is 0, so we can say that vector v2 is orthogonal to the vector e1. Now with the help of this vector, we can define e2. e2 can be defined as v2 divided by its norm. Now we will check e1 and e2 are orthogonal. So let us find the inner product of vector e2 with vector e1. Now substituting the value of vector e2. Now value of vector e2 is v2 divided by its norm. Now from here, this is scalar that can be taken outside of the product. So inner product of e2 with e1 is equal to 1 upon norm of v2 into inner product of v2 with e1. Now v2 and e1 are orthogonal vectors, so this product will be 0. Thus we have obtained two vectors e1 and e2 which are orthogonal vectors. Also let us check the norm of vector e2. Now by definition, square of norm of e2, that is inner product of e2 with itself. Substituting the value of e2 and taking the scalars outside, inside we have inner product of v2 with v2, which will be v2 norm square. So we get the quantity 1. So we have obtained e2 norm is equal to 1. So in the step 2, we have obtained the second vector e2 which is normalized, and also inner product of e1 and e2 is 0. Till yet we have obtained a set which is orthonormal and consisting of two elements. Now in the step 3, let us define the third vector v3, which is defined by x3 minus inner product of x3 with e1 into e1 minus inner product of x3 with e2 into e2. Now again this v3 is not equal to 0, because if we take v3 is equal to 0, in that case we get the three vectors linearly dependent. But actually we are given that these three vectors are linearly independent. So if we take v3 is equal to 0, we get a contradiction. So v3 is not equal to 0. Now we'll show that this v3 is orthogonal to e1 as well as e2. Now let us find inner product of v3 with e1. Substituting the values and using the properties, we have inner product of x3 with e1 minus inner product of x3 with e1 minus this is 0 and this is also 0. So we are left with inner product of e1 with e1 is 1, so that will be 1, and inner product of e2 and e1, that is 0, so that will become 0. So from here we have obtained these two terms which will be cancelled out. So we get v3 is orthogonal to e1. In the same way we can show that v3 is orthogonal to vector e2 by substituting the value of v3 here. We can see these two terms will be cancelled out, so we get the value 0. So v3 is orthogonal to the vector e2. Now we can define e3. e3 can be defined by dividing v3 by its norm. So we have obtained third vector of our orthonormal sequence. Continuing like this, in the nth step we can define the vector vn. Vector vn is given by xn minus inner product of xn with e1 into e1 minus inner product of xn with e2 into e2 and so on. The last is inner product of xn with en minus 1 into en minus 1. Now as we already discussed, n will also be not equal to 0, and that will also be orthogonal to the vectors e1, e2, e3 and en minus 1. Now we can define the vector en by dividing vn by its norm. So in this way we have obtained the nth vector of our orthonormal sequence. So this is the way to convert a given linearly independent set into an orthonormal set, and this process is called Gram-Schmidt procedure. Now next topic is the series related to orthonormal sets and sequences. So first is the definition. What is trigonometric series? A trigonometric series is a series of the form a naught plus summation ak cos kt plus bk sin kt. This kind of trigonometric series, that is also called Fourier series. Next definition is what is periodic function. If we take a real valued function x on the real line, then such function is said to be periodic if there is a positive number p, which is called period of the function, such that the value of the function x corresponding to t plus p is same as the value of the function x at t. Thus we can say that a function is periodic if it repeats its value after a particular interval of time, and that interval of time is called period of the function. Next is what is Fourier series. If we take a function which is periodic and having the period 2 pi and the function is continuous, then we can define the Fourier series of the function x by x is equal to a naught plus summation ak cos kt plus bk sin kt. This is called Fourier series, where the three coefficients a naught, ak and bk, these are called Fourier coefficients given by the formulas. A naught is 1 upon 2 pi integral 0 to 2 pi of the function x. ak is 1 upon pi integral from 0 to 2 pi of the function x into cos kt. bk is defined by 1 upon pi integral 0 to 2 pi x into sin kt, where k varies from 1, 2, 3 and so on. So these are the Fourier coefficients of the function x. Here, because the Fourier series converges for each t and it has the sum given in the form a naught plus summation k varies from 1 to infinity ak cos kt plus bk sin kt. Because the function x is periodic function, so therefore we can replace the interval of integration from 0 to 2 pi of any interval which has the length 2 pi. For example, you can use the interval minus pi to pi also. So we can take any interval which is having the length 2 pi. Now let us see an example how to find the Fourier series of a given periodic function. So we are given a function defined by having the value t on the interval minus pi by 2 to pi by 2, and over the interval pi by 2 to 3 pi by 2, this is the value pi minus t. Now we can see that the function x is having the period 2 pi. Let us find the Fourier series for this function x. Now by definition, Fourier series is given by a naught plus summation ak cos kt plus bk sin kt. Now we will find a naught, ak and bk, which are called Fourier coefficients. So firstly let us find a naught. Now by definition, a naught is 1 upon 2 pi integral. Here the interval is minus pi by 2 to 3 pi by 2, which can be split into two parts. First will be minus pi by 2 to pi by 2. On this interval, the value of function x is t, and from pi by 2 to 3 pi by 2, the value of the function is pi minus t. Now integrating these two terms and simplifying, you can see that the value of a naught, that will be 0. Now let us find ak. Now by definition, ak means 1 upon pi integral from minus pi by 2 to 3 pi by 2 of the function x cos kt. Now substituting the value of the function x on the two intervals, from minus pi by 2 to pi by 2, the value of function x is t, and from pi by 2 to 3 pi by 2, the value of function x is pi minus t. Now we can simplify these terms by using integration by parts. So first function is t, that will remain as it is. The integration of cos kt, that is sin kt divided by k, between the limits minus pi by 2 to pi by 2. Here first function as it is, integration of second, minus integral derivative of first function is 1, integration of cos kt, which is sin kt upon k. Here again using integration by parts, pi minus t as it is, integration of cos kt minus integral derivative of first function is minus 1, integration of cos, that is sin kt upon k. Now you can substitute all the limits and simplifying, you can see that the value of ak, that is 0. Now let us find the next Fourier coefficient, which is bk. Now by definition, bk is given by 1 upon pi minus pi by 2 to 3 pi by 2 x into sin kt. Now by using the definition of function x, which is given in the problem, so we get 1 upon pi integral minus pi by 2 to pi by 2. The value of function x is t here, and over this interval, the value of function x is pi minus t. Now again using integration by parts here, first function as it is, integration of sin kt, which is minus cos kt upon k, minus integral derivative of first, integration of second, derivative of t is 1, integration of sin kt is minus cos kt upon k. Here again using integration by parts, first function is pi minus t, that will remain as it is, integration of sin kt, which is minus cos kt by k, minus integral derivative of first function, which is minus 1, integration of second function, which is minus cos kt upon k. Now you can substitute the limits and simplify to get the value of bk, which is given by 4 upon pi k square into sin k pi by 2. Now we can see that if k is even, in that case this will become sin pi, 2 pi, 3 pi, 4 pi and so on, which will be 0. And if k is odd, the value of the function Euler coefficient bk, that is 4 upon pi k square into sin k pi by 2. Now we have obtained all the Fourier coefficients. We can substitute these coefficients in our Fourier series to get the value of the function x. Now next is the topic. We will find an expression for the Fourier series in terms of inner product. Now as we discussed, the Fourier series for the function x is given by a naught u naught t plus summation ak ukt plus bk vkt. Here ukt is cos kt and vkt is sin kt, and u naught, that will be cos 0, which is 1. As we already discussed in the last topic, that these two sequences, sequence UK and the sequence VK, these are orthogonal sequences in the inner product space of real valued continuous functions on the closed interval 0 to 2 pi. And in this space of continuous functions, we define the inner product of x and y by integral 0 to 2 pi x into y. Now, because also we can see that the sequence cos kt and sin kt, they are also orthogonal to each other for every j and k. Now, let us find the values of aj and bj. Now, to find these values, let us multiply this equation 1 by fixed uj and integrating over the interval 0 to 2 pi. So, if we multiply by uj and integrate from the interval 0 to 2 pi here, we can see that because uj and vk are orthogonal sequences, so the inner product of uj with vk, that is 0, means by definition of inner product, which we already discussed, integral from 0 to 2 pi, the product of the two functions. Now, because these are orthogonal, so inner product will be 0, so this integral will be 0. Also, u0 and uj, they also have their inner product 0 because the sequence is orthogonal sequence. So, these two terms, they will be 0. So, substituting the values in this term will become inner product of x with uj is equal to aj into inner product of uj with uj. Now, inner product of uj with uj means uj norm square. So, from here we can find the value of inner product of x with uj, which is given by aj into uj norm square. Now, if j will be 0, this will become u0 norm square, which is having the value 1. Now, if un, because un is orthogonal sequence, and if n and m are different here, we will get the value 2 pi. So, substituting the value here, we get inner product of x with uj. Now, similarly, we can multiply the equation 1 by vj, which is fixed, and integrating between the limits 0 to pi with respect to t. So, we get integral 0 to 2 pi x into vj is equal to, simplifying this integral again by using the same conditions, because uk and vj are orthogonal sequences. So, the inner product of the distinct members, that will also be 0. Also, inner product of uk with vj, that is also 0. So, we will be left only with this term. Now, again in this term, because this is orthogonal sequence, so when k and j will be different, this inner product, that will again become 0. So, we get value only when k and j are same. So, in that case, this is inner product of vj with vj, which will become vj norm square. Now, inner product of x with vj is equal to bj into vj norm square. Now, what is vj norm square? Because vj is orthogonal sequence, for distinct members the value is 0, and also for j is equal to 1, 2, 3 and so on, this value is pi. So, we have obtained the values of the coefficients aj and bj. Now, aj is 1 upon uj norm square into inner product of x with uj. Now, we can write this value in the form aj is equal to 1 upon uj norm into inner product of x with ej, because ej is given by uj divided by uj norm. In the same way, we can define bj given by the value 1 upon vj norm into inner product of x with ej bar. So, these are identical with the Fourier coefficients, which we define by the Euler's formulas. So, we can write the Fourier series of the function x in terms of the inner product, which is given by x is equal to inner product of x with e naught into e naught plus summation k varies from 1 to infinity, inner product of x with ek into ek plus inner product of x with ek bar into ek bar. So, this justifies the term Fourier coefficient as we used in the previous theorems like Bessel's inequality.